I'm Noah Savarpu, and I'll be presenting our CS224N project, which is Smart GPT-2 Adversarial Regularization for GPT-2 fine-tuning. Okay, so starting with the motivation. So we're trying to fine-tune large language models on a small data set, which is risky, and you can overfit severely. This is especially the case for our generation task, where we only have 143 training sonnets. Standard regularizers like dropout and weight decay help, but they don't directly address the smoothness of the learned representation space. So we're using SMART, which addresses this with two components. First, a smoothness term that adversarially perturbs the input embeddings and penalizes KL divergence between perturbed and cleaned outputs. It basically forces the model to be robust to small input changes. And then the second one we have is Bregman proximal term that maintains an exponential moving average of the previous model parameters, and it penalizes drift, so it acts as like a trust region constraint. And to rigorously evaluate SMART, we designed a 6-way ablation study applied to both tasks. Vanilla fine-tuning as our baseline, and then we had SMART S, which uses the smoothest term only, and SMART B, which uses the Bregman term only. SMART Full combines both. And then there's the dropout and the weight decay as standard regularization comparisons. Running all 6 models on both paraphrase detection and sonic generation lets us isolate exactly which components of SMART is driving a performance, if there's any performance gain. For paraphrase detection, we use GPT-2 medium with a closed stop prompt, classifying based on the last non-padding token, an implementation detail that was critical since naively using the last position caused accuracy to collapse to as low as 0.36 to 0.4. Looking at the results, SmartS and SmartFull both achieved 90.4 dev accuracy, the best of all 6 ablation modes, but we had vanilla and dropout tied for 90.1%, and then weight decay at 90.2%. And Smart B was the only method to fall below vanilla at 89.9%. Our best submission achieved test accuracy of 0.897, so the dev gains held up on the unseen data. One finding from the ablation is that we had SmartFull and SmartS achieve identical accuracy, but SmartFull takes 12% longer per epoch because of the Bregman proximal term. 0 measurable benefit, extra cost, so an early signal that the smoothness component alone is doing most of the work. Alright, so for the qualitative analysis, both models received the exact same prompt, and which was the first 3 lines of Sonnet 0. Vanilla's output breaks down completely, repeated tokens like concealed, tokenization artifacts, and meters that fall completely apart. SmartS maintains the archaic Shakespearean diction, coherent syntax, and attempts a structured couplet. So the qualitative gap directly supports the quantitative char-F difference. Also, the seed consistency figure is one of the most striking results in the whole study. SmartS converges to 41.52, 41.54, and 41.56 across 3 independent seeds, a standard deviation of just 0.02. That's 20 times lower variance than dropout and 28 lower than weight decay. This isn't just luck. All 3 seeds settle at essentially the same score, regardless of which epoch peaked during training. Now for our sonnet generation results. The bar chart shows best versus final char-F for each of the 6 ablation modes. Vanilla has the largest gap by far, 1.14 char-F points between its best checkpoint and final evaluation. The training loss plot explains exactly why. For all 5 regularization methods, training loss plateaus somewhere between 3.41 and 4.76 and holds there. Model quality is stable, and the char-F gap you see is purely sampling variance from the top P generation. For vanilla, loss fell from 4.6 all the way to 0.21 across 30 epochs. It never converged. It memorized the training sonnets. The char-F gap for vanilla includes genuine model degradation from overfitting on top of sampling noise. This is why the training loss columns is essential. Without it, all 6 methods might look equally well behaved, which would be completely misleading. SmartS achieves the highest mean, best char-F, at 42.44. After hyperparameter search on the dev leaderboard, tuning temperature, top P, and max generation length using the SmartS checkpoint from seed 11712, epoch 19, we achieved a dev char-F of 43.713 and test char-F of 43.529. Let's close with our conclusions. SmartS is the best overall method, best paraphrase accuracy, best sonnet ceiling char-F, and 20 times more reproducible than dropout, and 28 times more reproducible than weight decay. Vanilla overfits sonnets by epoch 29, more than 15 times lower training loss than any regularized method. Every single ablation mode beats at the end of training. Dropout and weight decay are competitive on raw char-F, but their high seed variance makes them unreliable for low resource generation. Smart B underperforms on both tasks, falling below vanilla on classification and ranking last among regularized methods on sonnet generation. This is because the Bregman proximal constraint over-restricts parameter updates on small datasets. Mentioned earlier, Smart Full is equal to Smart S in accuracy, but costs 12% more. And the key insight is that training loss, not just char F, separates sampling noise from genuine overfitting. And that's only visible because of our full 30 epoch 6-way ablation. Ultimately, Smart's smoothness objective is a meaningful upgrade over standard regularization for GPT-2 in low resource settings. Thank you.